Hello everyone, welcome to Computer Organization and Architecture class. In this unit, we will talk about mass storage. In computer systems, the main memory requires continuous power to retain the data stored, and thus, there is a need to use a mass storage media such as magnetic disk or optical disk to retain information indefinitely after the power is removed. A magnetic disk, also known as hard disk, is a device for storing information that supports a large storage density and a relatively fast access time. A hard disk is composed of a stack of one or more platers that are spaced close together and are connected via a spindle as shown on the left of the screen. Each plater has two surfaces. There is a moving read-write head flying on each surface of a plater as illustrated on the right. The read-write heads are attached to an arm which moves the heads in and out to reach different portions of the surface. The platers rotate at a constant speed of typically 5,400 to 15,000 RPM, which stands for revolutions per minute. The heads read or write data by magnetizing the magnetic material as it passes under the heads when writing, or by sensing the magnetic fields when reading. Only one head is used for reading or writing at any time, so data is stored in serial fashion, even though the heads can in principle be used to read or write several bits in parallel. When the read-write head uses Manchester encoding or modified frequency modulation to encode data as ones or zeros. In Manchester encoding, there is a transition between high and low signals on every bit, resulting in a transition within every bit period. A transition from low to high indicates a 1, whereas a transition from high to low indicates a 0. These transitions are used to recover the timing information. A single surface contains several thousand concentric tracks, which in turn are composed of sectors of typically 512 bytes in size, stored serially as shown on the right of the screen. The sectors are spaced apart by intersector gaps, and the tracks are spaced apart by inter-track gaps, which simplify positioning of the head. A set of corresponding tracks on all of the surfaces forms a cylinder, as illustrated on the left of the screen. Compact disc CD is arranged in a spiral format, unlike the magnetic disc is arranged in concentric tracks. In addition, CD rotates the disc with constant linear velocity, while the hard disk rotates the disc with constant angular velocity. Therefore, the speed of rotation of CD is adjusted so that the disk moves more slowly when the head is at the edge than when it is at the center. The hard disk storage capacity C can be computed using the formula as shown on the screen, where N is the number of bytes per sector, S is the number of sectors per track, T is the number of tracks per surface, and P is the number of planar surfaces that have data encoded in them. For example, assume a hard disk drive with 512 bytes per sector, 1,000 sectors per track, and 30,000 tracks per surface in 8 planar surfaces. The total capacity C of the hard disk is C equal to 512 multiplied by 1,000 and then multiplied by 30,000 and then multiplied by 8, which is around 123 gigabytes. The maximal data transfer speed of a hard disk drive can be governed by the following 3 factors. First, seek time, which is the time to move the head to the desired track. Second, rotational latency, which is the time for the desired sector to appear under the read-write head. Third, transfer time, which is the time to transfer the sector from the disk plater once the sector is positioned under the head. The performance of a hard disk is typically evaluated with the following 3 measures in the specification. First, the average seek time. Second, track-to-track seek time. Third, average rotational latency, which is the time of one complete revolution of a plater. Hard disks on the market is typically 5,400 or 7,200 RPM. In some high-end machine, you can see 10,000 or 15,000 RPM hard disk. We will use the following example to explain the idea. In a hard disk drive, assume the platers rotates at 10,000 RPM. The track-to-track seek time to move the head between adjacent tracks is 1 millisecond. There are 1,000 sectors per track that are stored in linear order, from sector 0 to sector 999. The head sees the sectors in that order. Assume the read-write head is positioned at the start of the sector 1 on track 12. There is a memory buffer that is large enough to hold the entire track. Data is transferred between disk locations by reading the source data into memory. Position the read-write head over the destination location and writing the data to the destination. So the first question is, how long will it take to transfer sector 1 on track 12 to sector 1 on track 13? And the second question is, how long will it take to transfer all of the sectors of track 12 to the corresponding sectors on track 13? We assume sectors do not have to be written in the same order they are read. To transfer sector 1 on track 12 to Sector 1 on track 13, the process includes Step 1, read Sector 1 on track 12. Step 2, move the head from track 12 to track 13. Step 3, weigh the Sector 1 of track 13 under the head. And Step 4, write to Sector 1 on track 13. First, the hard disk is rotated at 10,000 RPM, which indicate that platers spin 10,000 rounds in 1 minute. As you know that 1 minute equals 60 seconds, and which equals to 60,000 milliseconds. Therefore, platers will take 60,000 divided by 10,000, which equal to 6 milliseconds to spin a full revolution. Therefore, the time to read or write a sector is 6 divided by 1,000, which equal to 0.006 millisecond per sector. The track-to-track seek time to move the head between adjacent tracks is 1 millisecond as described in the scenario. And therefore, an additional 6 millisecond minus 0.006 millisecond, which equal to 5.994 millisecond of rotational delay is needed for the head to line up with Sector 1 again. The head movement time of 1 millisecond overlaps the 5.994 millisecond of rotation delay, and so only the greater of the two times 5.994 millisecond is used. We sum the individual time as 0.006 plus 5.994 plus 0.006, which equals to 6.006 millisecond. To transfer all of the sectors of track 12 to the corresponding sectors on track 13, the process includes Step 1, reorder sectors on track 12. Step 2, move the head from track 12 to track 13. Step 3, write OR sectors on track 13. First, the hard disk is rotated at 10,000 RPM, which indicates platers will take 6 milliseconds to spin a full revolution. Therefore, the time to reorder sectors on track 12 is 6 milliseconds, and the time to write OR sectors on track 13 is also 6 milliseconds. The track-to-track seek time to move the head between adjacent tracks is 1 millisecond. While the head is moving from track 12 to track 13, the platers are rotating 1 divided by 0.006, which equal to 166.7 sectors. This indicates 167 sectors have passed under the rewrite head. Thus, we can reposition the head as sector number 168 on track 13 and start writing. Since the sectors can be written in different order than they are read. And therefore, we can sum the individual times as 6 plus 1 plus 6 equal 13 milliseconds. The hard disk is relatively fast and can store high density of data. However, it is still slow comparing to the main memory in the system. Therefore, researchers at UC Berkeley investigated approaches to combine low-priced hard disks to behave as one large disk with faster access time and fault tolerance. These approaches are named RAID, which stands for redundant arrays of inexpensive disks or redundant arrays of independent disks. There are various ways of RAID configuration. We will only talk about the most commonly used RAID configurations as highlighted in red. RAID 0 refers to block level striping, which combines all disks as one big disk without fault tolerance. In this configuration, the RAID is more efficient because you can write your data onto several disks all at once. Similarly, when you need to read those data, each independent disk can read the data at the same time. RAID 1 refers to mirroring, which uses one disk to back up another disk. In this configuration, it is very safe, but you can only store data on half of the total disks. RAID 4, RAID 5, and RAID 6 configuration refer to block level striping with parity. They use Hamming Error Correction Code (ECC) to protect the data. Among them, RAID 5 and RAID 6 are commonly used. Where RAID 5 can tolerate one disk fail, and RAID 6 can tolerate two disk fail. RAID 10, also known as RAID 0 plus 1, refers to striping and mirroring, which combines even number of disks. Every two disks mirror each other. All mirrored disk forms a big striping disk. There are several online animated references to talk about the RAID configuration. Please watch the videos as listed on the screen. Any question?